Can you see my screen?
Huh, sir.
Okay, so today we'll start off a new topic in spatial data modeling and types. So what we are talking about whenever we are talking about a spatial data, we are talking about types. So what do you mean by spatial data? Spatial data are spatial data types needed to model geometry and to suitably represent geometric data in database. So what we are trying to do, we are trying to create a database related to spatial features. So what are those spatial features? These are point, line, polygons, maps, graphs, and this provide a fundamental abstraction for modeling the geometric structures of object in space, their relationship, properties, and operation. So it's an important part of data model and implementation of spatial database modeling system. So what is the definition of spatial database modeling system? The definition of SDT is to a large degree responsible for a successful design of spatial database model. Then you have got uh, decisively affects the performance of a spatial database system, exerts a great influence on the expressiveness of spatial query languages, and should be independent from the data model used by DMS. So what finally we can conclude from the above expression is the understanding of spatial database types is a prerequisite. Until unless you don't understand about the spatial data types, you cannot model it. And for an effective construction of important components of a spatial database management system like spatial index structure, optimizations for spatial data, spatial query language, storage management, graphical user interface, and for cooperation with extendable DBMS providing a spatial type extension package for spatial data blades, cartridges, the definition and the implementation of spatial data type is probably the most fundamental issue in the development of spatial data system. So this tutorial, what we'll be doing, we'll be reading the fundamentals of spatial database modeling, what are the spatial data models and type system, formal definition methods, tools for implementation of spatial data types, data structure and algorithm, and other interesting topics and the resource train. The tutorial on the basis of which I have framed my slides today is spatial data type for database system by fine resolution geometry for GIS Springer 1997. So today we'll be reading what are the foundations of spatial data modeling, what needs to be represented, or three-level model of phenomena in space, design criteria for modeling spatial data type, closure properties and geometric consistency, organizing the underlying space, equivalent geometry versus discrete geometric basis, ADTs in databases for supporting data model independence, integrating spatial data types into the DBS data model. So what needs to be represented? There are two views of spatial phenomena. One is object in space that tells about the entity orientation, feature-based view, that is vector data, spatial databases. Second one is space itself, that is space-oriented, position-based view that represents raster data or image databases. So when you talk about object in space, we are talking about the city area, we are talking about the population, we are talking about the roads, we are talking about the routes, we are talking about the highways. And when it comes to the space, the statement about every point in the space is the land use land cover maps, then partition into different state, districts. So all such things will be done using space model. So what we have to consider? We have to consider that modeling is a single self-oriented object modeling especially related collection of objects. So whenever we are talking about spatial data modeling, what we are talking about, we are talking about fundamental abstraction for modeling self-contained objects. So what are those self-contained objects? One is point data. Point data, like it will be stating about the city, it will be stating about the various temples, lighthouses. So they are the location of object in the space, but it's extent relevant. Next one is line, that is a highway, it can be rivers, it can be cables, it can be routes and connections in space, movement through space. And region, where we'll be going to extent of an object relevant, like what is the city, what is the lake, what is the district boundary, what is the forest boundary. And fundamental abstraction for modeling spatial related collection of objects are partition of the data. So what we have to do, you have to partition of the data will be done like land use, district wise, ward wise, country wise, speech area, then spatial embedded networks like highway, railways, rivers, electricity, phone. So all such data has to be handled. Not only the data, we will be handling the 3D data itself in space, like structural modeling. If you are going with the structure, can be sets, it can be sequences, it can be partitions, it can be operations. Generally, the kind of operation that we do is overlay analysis, shortest mean path. So whenever you are performing such kind of analysis in GIS, such operations are is considered to be as structural modeling. Then you have got object based modeling, where you will be spatially referent object will be connected, its population name, city name, location, a date, area name, flow line, path name, all the data has to be labeled. Then you've got a spatial modeling, where you will be creating the point data, line data, polygon data. And spatial data types are point data, line data, polygon data, and operations are point in polygon text, intersection, union. So whenever you are going for designing of criteria for modeling spatial data types, so whenever you are going for the modeling, the important parameter for the uh, designing of spatial data modeling is ki first you have to define what is your objective, then you have to define about the data model independence, ki how independent the model is, then extendability, what are the different kinds of data format that you are going to expect, then efficiency, how efficient your model is, what kind of operations you'll be performing, whether you'll be performing vector based analysis or you'll be performing the raster based analysis. Then you will be seeing the geometric consistency, because whenever you are going for any kinds of spatial measurement, we are going for its spatial location, and for that the spatial connectivity, the geometrical contingencies, consistency is very important. Then you will be going for various kinds of finite resolution, numerical robustness, topological correctness, formal definition, and finally the closure properties. So when you are talking about the closure properties and geometric consistency, we are talking about general definition and structure of spatial data objects. Like when you are going for this kinds of operation, we'll be going into the point into polygon, line into line, point into polygon operation. So a spatial object must be closed under a set of operation on the underlying point sets. So the support of geometric contingency constraints for spatially related objects. What are the objects that are as adjacent to what feature? So left polygon, right polygon, upper polygon, lower polygon, left arc, right arc, what is the node, what is the vertex. So all such properties has to be stored in your spatial database modeling, where the STT, spatial data type, defines much of or facilitates to offer consistency constants. So whenever you're organizing the underlying space using Euclidean geometry versus discrete geometrical basis, Euclidean space is a continuous feature that is based on conceptual of geometric algorithm, but the computer numbers are finite and discrete, that is x and y, that is a real data. So whenever you're putting the numerical rounding errors and the topological inconsistency, then what you have to do, like this is the point D. So with this point D is on A, or is D properly contained in the area below A and B, or what happens if the segment of C between D and D dash. So these are the different kind of conditions that will be generated, or such kinds of questionnaire will be created whenever you are going for any kinds of statistical analysis in spatial data modeling. And for that, formal SDT definitions must be in the mind the finite representation available in your computer. So to avoid the computation of new interaction points with geometric operation, first you have to define the spatial type and operation, and second one is for treatment of those numerical problem upon updates on geometrical basis. So there are two different approaches that generally we are applying in whenever we are talking about spatial data types and modeling. One is simplical complexes and next one is realms. So we'll go, okay, what is simplicical complexes? One is topological relationships are separately recorded and independent of metric position. So what they are created? They are created as a independent user. Use of k simplices for representing minimum spatial object for dimension k. Construction of rule: k simplex consists of k plus 1 simplex of dimension k minus 1, which is a component of simplex, which is called a phase. So you can see point is a 0 simplex, a line is a 1 simplex, polygon is a 2 simplex, and when you are going to a 3D feature, that is a 3 means 3 simplex. So what does this says about? So there are two completeness principles when you are seeing the above example. One is completeness of incidence, which says that the interaction of two case simplements is either empty or face of both. Simply says no line intersection at the point which are not start or end points of a line. No two geometric may exist at the same location. Secondly is completion of inclusiveness. One is every case simplex is a face of k plus 1 minus simplex, means all the points are endpoints of lines. All the lines are boundaries of a triangle. No isolated points, no lines which are not of boundary. So these are the simple complex means finite set of simplies such that the interaction of any two simplies is empty or a phase. So these are the correct simplical complexes that we are creating, and these are the wrong simplices creating. Means shapes what we are creating. We are talking about the shapes. So what is the advantage? The advantage is maintenance of topological consistency. Then approach fulfills closure properties. The drawbacks is no spatial algebra has been defined on the top of this approach. Triangulation of space would lead to space consuming representation of spatial objects. No treatment of numerical problems. Additional data structures needed to be realized. The next one is Relims. So what is Relims? You can see how you are putting the data sets into point, line, polygon. You're creating, you have created a polygon A and B, and then you are creating the different attributes, the line features. So what does it says? It says description of complete underlying geometry, means all points and all lines of an application or a application space. So what does it says formally? A finite change of points and non-intersecting line segments defined over a grid such that each point and each point of a segment is a grid point. Each endpoint of a segment is also a point of realm. The no realm point lies within a segment, and any two distinct segments do neither properly intersect nor they properly overlap. So you can see that these are the errors that you are creating. If you are causing it, this is an error. If you are just leaving it without joining, that is a error. So a realm is a spatially embedded planar graph. So all the numeral problems are treated below with the realm layer. That is the input. Input says the application of the data are sets of points and intersecting line segments. Output says the realmified data that have become acquainted with each other. The basic idea is slight distort both segments. So what is the best solution if you see to the current example ki how these segments are created? So the best example is intersection of segment A with some further segment C. What are the observation? What you can observe from the current example is the segments can move far away from their original position by iterated interaction, and the topological errors can occur. Point P is now on the wrong side of A. So what we are stating that there can be various kinds of errors when you are redrawing the same segment. So what you have to do, you are caught within the envelope and can never cross a grid point. So what are the advantages of this concept? One is definition of distinct spatial data type on a common current domain, guarantees of closure properties, then protection of geometrical computation in query processes from problems of numerical robustness and topological correctness, enforcement of geometrical contingency of related spatial objects. What are the disadvantages? No spatial database types operation is possible that can create new geometrics like leave the rim closure like convex, then interaction of realm into database system somewhat difficult. So it is important to use ADTs in databases for supporting database model independence. What are the different kinds of modeling aspect? One is separation of DMS data model and application specific data types and algebra. Second one is modularity, conceptual clarity, then reusability of ADTs for different DBMS data models, then extendability of DBMS data models. Now, implementation aspects comprises of modularity, information hiding, exchange of implementation, employment of specified methods, efficiency of data structure for data type, and algorithm for operations. And finally, integrating the spatial data types into DBMS data model. So what you have to do, integration of single self-contained spatial objects, like it can be realized into a data model independent way like ADTs. Basic concepts suggest represent spatial object like point, line, polygon by objects of the database model data model with at least one SDT attribute. Means DBMS data model must be open for new user defined types, that is ADT support, data model independence and extendability. So what you are to do, we are going to create a relational model where we'll be saying relation states. The state name will be as a string, area will be a region, and your populations connected to that state level will be in the form of integer. Then relation, again state is related to cities, the city name will be string. String means alphabets. Center means when we are saying about cities, they are the point location. So your center will be a point. Then your extension, the area will be in the form of region. And finally, the total population will be in the form. Population will be always in the form of numbers. Numbers are integers. And finally, relation, rivers, like there is a river. So river name will be string, and the route through which it is flowing. So what you do, you create line. So route will be line. So integration of spatial related collection of objects. No data model is independent. Partition is done, and that set of database with region attribute, loss of information, disjointness or adequacy of regions cannot be models. So no support of this integrity constraint by DMS. Network, not much research on spatial embedded network has been done with graph database with explicit graph integrated into OO model. So what are the different kinds of spatial model? Types and system. So spatial data types are single self-contained object like point, line and region. Spatially related collection of objects are partition and networks. Spatial operations are spatial predictness, returning Boolean values like topological relationships, that is, equal, unequal, disjoint, adjacent, neighboring, intersect, overlap, meet, touch, inside, outside, covered by, contains. So these all are topological function that you will be performing. You are doing whenever you're doing any kind of topological exercise that you're doing in ArcGIS, whenever you're creating a topology, then metric relationship, what is in circle, what is in window, then spatial order and strict order relationships, that is what is behind, what is in front of, what is above, what is below, what is over, what is under, what is inside, what is contained. And directional relationship means whenever you are creating the spatial predictness, this all property must be seen. What is on the left, what is on the right, what is on the north, what is on the south. Then spatial operation returning numbers like area, parameter, length, diameter, district, maximum districts, direction, components. Then spatial operation returning new spatial objects like object construction operation like union, intersection, difference, convex, center, boundary, border, boxes. Then object transformation operations like extend, rotate, translate. Spatial operations on sets of spatially related objects like what are the general operations, who is the closest, what is the composed, what is the decomposed. Then operations for partitions like overlay, superimposition, fusion, cover, windowing, clipping. Operations for network like shortest path. These are the various kinds of classification data types. Now we have got different classification models like concrete models. Under concrete model, you have got point-based model. Example, jurisdictional, Abra is there. Then complex region with holes. Then topological relationships. Then linear constant approach. The different scientists have given different models like Gutting in 1988 given a georelational algebra. Warboys and Mofakos in 1993, complex regions with holes. Eckhofer and Haring 1990, Eckhofer and Franz Josa in 1991, topological relationship. Belushi, Bottino and Catina in 1997, and Gurmach, Ragox and Segufin in 1998, linear constant approach. Descript model was given by Gutting and Schneider in 1995 that gave us rules algebra. Then Frank and Kuhn 1990, 1986. Then again Hofford, Frank and Jackson in 1998 provided us simple based models. These are the name of the scientists who have generated those spatial data models, and their name these models are locally known. Then abstract model suggests the logic, the pointless axiomatic models like spatial logics. So the examples of spatial data types for single spatial object, that is Gutting relational algebra, that is based on point set theory, that says that the relational algebra viewed as multi-sorted algebra means having the relationships plus atomic data type. So what are the kind of data sets that can be sorted? One is integral data, real data, string data, point data, line data, polygon data, area. Then examples of relation, that is states. You'll be writing the state name as a string, extension as area, and population as integer. A point value is a single point, a line value is a polyline, and a polygon value is a polygon without holes. So spatial type era for modeling partition constraints are maintained by system but by the users. So when your generalization equals polygon comma area extension equal line comma region, and geo relation is point comma extension. So whenever you are going for the geometrical predicts, that is equal not equal to, then inside then you've got intersection, then is neighbor of. So such kinds of operations are performed. Then you've got geometrical relationship operation like intersection, like line into line, then line into region, then polygon into region, then for overlay area into area, then what is his extension will be point, then Voronoi point into region equal area, closest point into point relation. So these are the various operations that we are performing for operating during atomic geometrical objects like convex hull. Center, convex hull is a point. At last, you will be getting a polygon. Center means point. Point extension is point. So this is how it looks like when you are using such models. So operation returning numbers, that is distance is point into point, that is a real. Then you have got diameter point is a real, length line is a real, parameter area region is a real. So when you are comparing the different kinds of criteria, you have to see the general definition, you have to see the closure properties, then you have to see the formal definitions, finite, precision, arithmetic, support of geometric consistency, efficiency, extensibility, data model independence, then remarks only simple polygons, no union, difference of polygons forming the intersection of two spatial objects must be embedded in a relation operation, no numerically critical operations included, simple data structure and algorithms. Now, the second definition given by Warburg and Foucault in 1993 is based on point-set topology that says that complex spatial region with holes and islands within the holes at finite level, atom is subset of IR square, that is a topological equivalent to a closest disk. Base area aggregation of atoms which are structure is described by skeleton graph. What are the constant? Constants are the intersection of any two distant atoms is either completely or a singleton set. This is a composite object, has no holes. So you can see that how this recursive construction of complex spatial region is being created using such method. So the what is the constant? Constant is for each vertex, their successors form a base area for each vertex V not equals to root, and each successor W of V holds A, V and B. The intersection of W and boundary of V has finite cardinality. So the operations that we are performing is equals, intersection, union, difference, boundary, adjacent, centroid, area, parameter, components connected. So the comparison of various basic designs, general definition, closure properties, formal definition, no finite precision arithmetic, no support for geometrical contingency, efficiency is question mark, extendability is a question mark, data model independence is available. So what we are reading the different spatial database models. Then you have got Hack 44 and Haring 1990 two based on point set topology. The goal is a complete collection of topological relationship between two spatial objects. The topological relations are invariant under translation, rotation and scaling. Then originally topology relationship between two simple connected regions without hole. This is a boundary and an interior. Then four intersection models like four intersection sets between boundaries and interiors of two objects. Extension 9 intersection models consider all intersections with exterior and complement includes point and line features. Then you have got four intersection models like this is equal, this is disjoint, this is covered by covers, overlap, meet inside the content. So this is the condition that we are putting. The relationships are A and B are disjoint, A and B oblique B inside A inside B oblique B contains A and B meets, A and B equal, A covers B oblique by divided by B covered by A covered underscore by B covered by A and B. So you have got different 16 combination. Out of this only 8 are valid. So out of you have made 16 combination with different intersection model, only 8 are valid. So the dimension extension method considered by Scientists Felice and Van Oosterom in 1993 provided a empty 0D, 1D, 2D in 2D space. This is 4 to the power 4 equals 256 combination for each relation group, that is for area by area, line by area, point by area, line by line, point by line, point by point, total 52s are valid. So too many relationships are to be remembered. Alternatively, what you can do, you provide the five basic relationship, that is touch, in, cross, overlap, disjoints plus three operators B, F, and T to obtain the boundaries. So what one can prove? One can prove that five relations are mutually exclusive, and five relationship plus three boundary operators can distinguish all these 52 combinations. So next model is Belusky-Barreto in 1997 gives the basic idea of spatial constant model, which represent spatial objects finitely as infinite collection of points satisfying the first order formula. A convex polygon is the intersection of a finite set of half planes, that is a conjugations of the inequalities defining the each half plane. A non-convex polygon is the union, logical disjunction of a finite set of convex polygons. So you can see these polygons here, how they are half plane representation. What is convexification of a polygon with a disjoint component. Then you have a convex with holes normal form. So finally you will see that if you compare the design criteria, the definition and property is good, formal definition is good, finite precision arithmetic is good, support for geometrical consistency is good, but efficiency, extendability, and data model independence is at a questionnaire. To solve this problem, Gutting and Schneider in 1995 provided the Rose algebra that is based on discrete geometric biasness. Rose is robust spatial extension. So the system of frame-based spatial data type, that is point, line, and region, whose objects are composed of real elements like points and segments of a discrete geometrical domain, that is a point value, a line value, or region value. So Rose algebra offers a comprehensive collection of precisely defined operations for manipulating such values like extension lines of region, then geo point extension, then inside geo into regions equal bull, then edge by vertex inside region into region bull, then area by edge by discount disjoint regions into regions bull. So you can see the different kinds of Rose algebra contains different operations which are usually numerically criticals. So closure properties are fulfilled for intersection, union, and difference due to general definition of spatial data types like intersections, point into point, that is a point, intersections, line into line, that is a point, then intersection regions into region is a region, intersection that is region into line, that is line, then plus and minus geo into geo equals geo. Then you've got spatial operations for manipulating sets of spatial related objects, that is database objects defined by general object data model, that is sum. Then you've got closets, other operation of vertices, contour, interiors, number of components. So you'll see that when you compare this design, the general definition, the closure properties, the formal definition, the finite precision arithmetic, support for geometrical consistency, efficiency, extendability, data model, all are available. Then Q and Randall in 1996 provided the logic. The logic is pointless approach, that says regions are the basic indices, no points, no lines. Then axiomatic approach to represent and reasoning about the topological spatial database models. You can see what are the different kinds of axiomatic formulation of topological formations, relationship where x is disconnected from y, where x is a part of y, x is indicated with y, x overlaps with y, x partially overlaps y, X is extremely externally connected to Y. X is a tangential proper of Y. X is a non-tangential proper than part of Y. So this kind of topological model is used to interpret the theory which says that C holds when the topological closures of regions X and Y share a common point. So similar results like Equafor et al. 8 mutually exhaustive and pairwise disjoint relationship. So what are those disjoint relationship? One is DC, disjoint, then TPP, covered by, then inside, contains, then EC meet, then covered by, contains inside, then overlap, then equal. So you can see that design closure definition property is questionable, efficiency effectiveness is also questionable. And last, we will be coming for the partition. Partition is nothing but subdividing of the plate into pairwise disjoint regions where each region is associated with an attribute having a simple or even complex structure. Partition implicitly models topological relationship, neighborhood of different regions which may have common boundaries, disjointness of different regions except for the boundaries, then application of a specific operation. So you can see that when you are performing this overlap, so what is the expected outcome? So you can see this is the outcome after running this operation. When you are going for a superimposing operation, you will be seeing how the final product is seen. Then you are going for a window, it is the final product. Then same is for the difference. So the other operations reclassify cover and clipping. So Skoll and Weissert in 1989 goes for identification of application specific operations on the map, complex object algebra extended by a data type for regions plus some operations on regions, that is union, intersection and difference. A map is the set of tuples with a region attribute, elementary region like single polygon, region, sets of polygons. Problems are region type, not closed under union operation, no control on partition constraints through the model, deeply data dependent. Then you have got another model which say formal definition of spatial pattern. Basic idea is a partition is a mapping of y square to some label type, that is regions of a partitions are assigned single labels, adjacent regions having different labels in their interior. A boundary is assigned the pair of labels of both adjacent regions. So there are three powerful operations that are closest under partition and are sufficient to exploit all the known application specific operation. The first one is intersection, that computes the geometrical intersection of all regions of two partition and produce a new spatial partition. Each resulting region is assigned the pair of labels of original two integrating regions. Labels on the boundaries are derived correspondingly. Then you have got an operation that says relabel, that is changing the labels of the region of a partition either by remaining the label of each region or by mapping distinct label of two or more regions to a new label or adjacent label in the result partition are fused. Refine that looks with finer granularity on regions and reveal the enumerate the connected components of the region. And finally, you have got a formal definition methods. What are those formal definition methods and why you are requiring such definition? It is important for better understanding of the complex semantics of spatial objects and operations at designers level. Formal definition of SDC should be directly usable for a formal definition of corresponding spatial operations, clarity and contingencies at the user level, consideration of the fitness of computer and problems of numerical robustness and topological correctness. A first step towards a standardization of spatial data types, formal applications, specification of SDTs for a possible realization at the implementation level. So what are the different kinds of theory? One is point set theory, which says basic assumption that says space is composed of infinitely many points and contains a set of spatial objects. Each spatial object can be regarded as a point set occupied by that object. Analytically, geometry is used to represent structures like point, line, polygon by the numbers and relations between these structures by equations. Use of set operations for constructing new object. Topological properties are deduced from analytical geometry by numerical computation. Then two main problem of this two are possible anomalies is missing points, then missing boundaries, then dangling line, dangling point, missing chords. So these are the two intersecting region objects that you can say this is a error. Then conventional intersection, again this is a error, and this is regularized intersection, this is also error. Next is point set topology, which suggests that it has some basic assumption as point set theory and investigates topological structure of a point set data. It also investigates properties that are independent of an underlying distance or coordinate measures that are preserved under continuous topological transformation. Regularization of point sets to avoid anomalies, which leads to spatial objects as regular closed sets. Then geometrical operations are equated with regular set operations. Then you have got finite set of theory, which says definition layers of roles and realms by Gutting and Schneider in 1993 and 1995. So the rows algebra operations for the object operation, we go for the inside, edge inside, what is inside, area disjoint, edge disjoint, disjoint. So you can see the various kinds of operations that are being supported for the various layers like spatial data types and spatial algebra primitives, where the data sets are union, intersection, difference, edges, vertex, area, edge join, what is disjoint, meet, adjacent, intersect, encloses, on boundary. Then you have got different realms based structure and realms based primitive. What are the object operations that you will be performing? You will be performing R point, R segment, R cycle, R phase, R unit, R block, that is on, in, out, area inside, edge inside, vertex inside, area disjoint, is disjoint, vertex disjoint, adjacent, mean, includes, intersect, distance, area. So these are some of the problem sets that will be identifying such pairs, such graphs, will be preparing. And finally, the other formal approaches are algebraic topology that describes the structure of a topological space by a algebraic system. It is not based on general set theory, uses properties that are invariant under topological transformation. Topological properties are explicitly recorded, simplex concepts of boundary and interiors. Then order theory, lattice theory that allows the comparison of two or more sets of a set that can be used to answer the queries of inclusion and containment. Strict order for modeling a hierarchy of elements of a set, subdivisions of space into regions, perspectives, partial order for combining several hierarchies of space, relationship between distinct and cultivation areas. Then you have got constant approach where the first order logic with a point set interpretation. Then you have a constants are linear equation and equities. Then you've got a spatial logic that are pointless approach regions as basic entities, Clark's calculus of individual based on connections. And what are the tools? The tools and the data representation is implementation of spatial data system, spatial algebra, so that it can be integrated into DBMS for query processing, for storage management, for user interface and fulfillment of different criteria. And finally, we'll going for the representation of the type, data structure, algorithms for the operations. So DBMS view in SDT values is like treatment like values of the other types with respect to generic operations like access, use in schema, bulk loading, data exchange, user interface, values of varying and possibility large size, persistent storage on disk, in one or more pages, efficient loading into the main memory. Then the algebra view of SDT is complex data structure, use as a value of programming language type, support of computational geometry algorithms, no spatial support for each single operations means no most efficient algorithms, no sophisticated data structure, reconcile the various requirements of different algorithms within a data structure of each types. So you can see that the support of DMS value. No user of a pointed data structure in the main memory, use a page oriented data structure accommodating the DBMS support for a large attribute values or long phase. So you can see this is a small value and this is the larger value. So separation of a SDT value into part of small fixed size and extract geometry, part of possibility large varying side. So the support of algebra view help us to representation of contains approximation in the form of info. Then a representation contains stored values in unary functions like area, perimeter, length, number of components in the info part, and representation contains plain sweep sequence in the geometric part. And finally, the general marks is use efficient algorithms for computational geometry. This is a single step check approximation, look up stored functions value, use plain sweep. So these are the few examples of classical plane sweep needed complex. Then you've got parallel scan on two sequence of half segment plane, and the other important research that you can go and see for the scientists who are immediately working on different models, that is multi-scale modeling, cartographic generalization, three-dimensional spatial data modeling, spatially embedded graphs, then combination of space and time, spatio-temporal database, moving databases, then combination of space and uncertainties, spatial objects with impurities, intermittent, broad boundaries, vague objects, fuzzy objects, and these are few of the references that we have taken for the current study. So today we have covered with the different kinds of spatial data models, spatial data design, spatial data designing, the merits, the demerits, the logic, the intersection, the various names of the persons who have developed the various schemes, tools, the advantage, the disadvantage, and with this, I'll complete my today's presentation, and we'll have 4 minutes of or 5 minutes of group discussion followed by your LMS in your quiz in your LMS. Thanks for being patient.